Hello, dear friends. How are you?
Good morning, Doctor. How are you? I
Thank
am
you.
fine.
Good
Thank you.
morning.
Good morning, Victor. How are you?
Thank you. Thank you. Good morning. Okay. Uh, Let me start our today's.
Good morning.
Good morning, Mr. Abdullah. Let me start our today's class. In the previous session, I talked about the general details about your course, and I explained some I explained uh, some notes about your syllabus in this course and your exams and main references of this course. Also, I talked about some basic definitions about ordinary differential equations and their numerical solutions. I explained that a numerical solution uh, for an initial value problem related to a first order ordinary differential equation can be defined in this form. If we have some discrete time points, we want to obtain some values named y1 to yn, and these values will approximate our unknown function y at this time nodes. Also, I mentioned to some real-world applications resulted to ordinary differential equations. If I want to explain clearly, we talked about a pendulum, and based on some physical rules, finally we can obtain a second order ordinary differential equation subject to these two initial conditions. Here, our independent variable will be x, and dependent variable or our unknown solution will be theta. Theta in the movement of pendulum will be the angle between the trajectory of our pendulum and this vertical line, and we can obtain these values called theta. Also, I mentioned another example in the ecology, the relation between the population of predators and prey in an ecology. We saw that this system of two ordinary differential equations subject to these two initial conditions. This is the initial populations of predators, and this is the initial condition, initial population of prey in our ecology. And this system of this initial value problem of these two ordinary differential equations will explain the population of predators and prey and the relation between these two populations in our ecological environment. But these are some examples about where in the real world we can see ordinary differential equations in our mathematical modelings. But in this session, I want to continue the basic definitions about ordinary differential equations, and I want to explain some new details about how we can solve an initial value problem related to an ODE. After that details, we will start our numerical techniques to approximate the unknown solution of our problem. Okay, here in this remark, I want to explain about how someone can reduce a higher order ODE to a first order ODE. Let me consider this mth order ordinary differential equations. Based on our definitions in the previous session, this ODE will be from order m, because the biggest order of the derivative of our unknown function z subject to our independent variable t in this equation is m. This is the biggest biggest order of derivatives in our ODE. So this ODE will be an m order ordinary differential equations. I want to reduce this equation to a first order ordinary differential equation. So our main equation is from order m. I want to reduce this equation to a first order ODE. To this end, let me define some new variables. We will define y1 equals z, also y2 equals z prime, also y3 equals z double prime, up to this variable ym equals the m minus 1's order derivative of z. So we have m new variables, y1, y2, y3 up to yn. You can see y1 is equal to z, but the other variables y2 to ym will be defined based on the different orders of derivatives of z subject to t. Now we have this system. You can see y1 equals z, and z prime equals y2. So we can result y2 equals y1 prime, because y1 is z, y1 prime equals z prime equals y2. So y1 prime equals y2. Also, from these two relations, you can see y2 prime will be z double prime equals y1 double prime. So you can see y2 prime equals z double prime. Z double prime is equal to y3. So we can result y2 prime equals y3. You can continue this procedure, and finally you can see ym prime will be ym prime will be the first derivative of z m minus 1. So we have d, you can see this, we have z m minus 1 prime. The first derivative of m minus 1's derivative will be equal to mth order derivative, zm. So ym prime equals zm, and based on our main definition, main equation, zm equals g of t z prime to zm minus 1. So zm equals g, ym prime equals zm. So we can, from these two relations, we can conclude ym prime equals g. So here we have a system. y1 prime equals y2, y2 prime equals y3, up to ym prime equals g of x, y1, y2 to yn. Okay, now here we have a system of first order equations. All of these m equations will be from order 1, because all of these equations, in all of these equations, the biggest order of derivative will be first order. If we consider some initial conditions for this equation in this form, these are our initial conditions. Initial conditions. These are our initial conditions. We defined initial conditions in the previous session. The values of our unknown variable or variables at the starting point of our domain, it is 0 in this example, will be our initial condition. In the other words, our problem will be initiated at 0, and we are the values of z at this initial point 0. So these are our initial conditions. Here we have m initial conditions. How we can relate these initial conditions to these new variables y1 to yn. Based on these relations, y1 at 0 equals to z at 0. So y1 at 0 equals z0 and z at 0 will be c dot. So y1 at 0 equals c dot. Similarly, y2 at 0 will be z prime at 0, and this is c1. Continuing this process will result ym at 0 equals, based on the definition, equals zm minus 1 at 0, based on this definition. Ym at 0 equals zm minus 1 at 0, and zm minus 1 at 0 equals cm minus 1. So here you can see m initial conditions for these m equations. So here our higher order ODE or mth order equation is reduced to a system of m first order equation subject to these m conditions: y1 at 0, y2 at 0, up to yn at 0. This will be a first order system, so we can reduce any higher order ODE to a system of first order ODEs. If we have these initial conditions for our higher order ODE, we can obtain these initial conditions for this system of first order equations. This is the details about how we can reduce any higher order equations to first order equations. Okay. Now, in this part of our lecture, we want to talk about the main theorem of the field of ordinary differential equations. In the previous details, we saw that ODEs occur in many mathematical models in different branches of science and technology. But in many cases, we do not know the exact solution of this ordinary differential equation. So we want to focus on some numerical techniques to obtain some approximations of these unknown exact solutions. And the aim of this course is obtaining these numerical techniques and these numerical solutions. To this end, let me consider this first order differential equation. In the previous slide, I explained that every higher order differential equation or higher order ordinary differential equations can be reduced to a first order differential equation. So it's logical to focus on this first order differential equation, because when we obtain a numerical technique for these first order equations based on these details, we can extend this technique for any higher order equations, because there there is a relation between higher order equations and first order equations. So it will be good if we focus on first order equations, because the solutions of these first order equations will result the solution of any m order equations. So we have this first order ODE y prime equals f of x and y. Here f is known, x is our independent variable, and y is our dependent variable, or our unknown solution. We want to obtain y satisfying in this equation. To this end, in many cases, we need to consider a suitable initial condition for this equation. Let x naught and y naught be two given numbers. So, if we have the value of y at x naught equals y naught, then this relation will call initial condition for this first order ODE. In the other words, for a first order ODE, we need an additional condition. This condition will be this relation. If we have the value of y at the beginning point x0, then this value will call initial condition for this ODE. So in the rest, we want to obtain or numerical techniques for the first order ODE. Number 1, subject to initial condition 2. These two formula y prime I think I was disconnected. Do you have my voice? Is there anyone in the class? Do you have my voice?
Yes, Doctor.
Yes, Doctor, no problem.
Okay, okay. Okay, I was disconnected from this virtual class, and now we can continue our class. Okay. I was explained some details about Picard's theorem. I mentioned that we want to solve this first order ordinary differential equation subject to this initial condition. In the next theorem called Picard's theorem, we want to search, we want to investigate the unique solvability of this ordinary differential equation subject to this initial condition. We will see, according to some conditions, our ordinary differential equation subject to this initial condition will have a unique solution. But before we start to explain the Picard theorem, we need to define the Lipschitz condition for a function. Let's we have a function f of t and y. This is the function in the right hand side of our ODE. For any function f of t and y, the Lipschitz condition in the domain of D will be defined in this form. If a function, if for any values t and y and t and z in the domain of our problem, we have this relation. The absolute value of the difference between f of t and y and f of t and z be less than or equal to L times the absolute value of y minus z. This will be called the Lipschitz condition for function f. So, for any points t and y and t and z in our domain, if we have this relation, then we will say function f will satisfy the Lipschitz condition. Here, L, capital L, is a constant and will be called Lipschitz constant. For example, consider this two variable function f of t and y equals 2 over t times y plus 2 squared times e of t. Our domain will be these values t and y such that t is between 1 and 2 and y is between -2 and 5. We want to investigate the Lipschitz condition for these two variables function f of t and y equals 2 over t times y plus 2 squared t of t. Let t and y1 and t and y2 be two arbitrary points in our domain D. t and y2 and the absolute value of y1 minus y2. Based on the definition of function f, we have this relation for t and y1 and this relation for t and y2. Now, with some algebraic computations, or easily we can see here these two terms will be deleted, and subject to these remain values, we can see the results of this difference between in this form. Now we have 2 over t, the absolute value of 2 over t times the absolute value of y1 minus y2. Here the domain of problem is t between 1 and 2. So 2 over t will be less than 2 over 1, because in this domain the smallest value of t will be 1, so this fraction will obtain our biggest value at the point t equals 1. So this will be less than 2. Based on this relation and substituting in this inequality will result finally this relation. F of t and f of t and y1 minus of f and f of t and y2 will be less than 2 times the absolute value of y1 minus y2. This will be the constant value L, or Lipschitz condition, and this inequality will be the Lipschitz condition for any 2 points t and y1 and t and y2. We resulted the absolute value of f of t and y1 and f of t and y2 will be less than 2 times y1 minus y2. So we can result function f satisfy a Lipschitz condition on this domain D with Lipschitz constant L equals 2. So we can see the Lipschitz condition is very clear concept, and to check this condition, we will work similar to this relation. Now we are familiar with Lipschitz condition, and we are ready for explaining the famous Picard theorem. This theorem was proposed by Professor Picard, and he explained the details of this theorem and its proof. Let me read this theorem. Suppose the function f is a continuous function subject to its arguments t and y, or x and y, on this rectangle. R equals the points x and y when x is between x dot and xm and y minus y0, the absolute value of y minus y dot is less than ym. Here xm is greater than x dot and ym is a positive constant. Also, suppose this function satisfies this Lipschitz condition. F of t and y minus f of x and z is less than L times y minus z. Here L is our Lipschitz constant and R is our domain defined here. Also suppose that we have this final condition m times x m minus x0 is less than ym. So we have some conditions. Let me review these conditions. F is a continuous function. We have this domain for this function f. Here we have this Lipschitz condition for function f, and finally f we have m maximum of function f on this domain. Then we have this condition m times xm minus x dot is less than or equal to ym. So here you can see a relation between xm and ym defining this domain or defining this domain, and m maximum function f. Now, based on all of these conditions, we can resolve there exists a unique continuously differentiable function y defined on the interval x0 and xm such that this function will be the solution of the initial value problem 1 and 2. In the other words, based on the conditions of Picard theorem, we will have a unique solution y satisfying in this ordinary differential equation subject to this initial condition. So the Picard theorem. So Picard theorem will explain the main conditions needed to unique solvability of ordinary differential or initial value problems y and 2. The condition 3 is called Lipschitz condition. L is our Lipschitz constant, and here we have this theorem, but we do not want to explain in details the proof of this theorem. If you are interested about the theorem about the proof of this theorem, you can study our reference books. But in this course, I do not want to explain in details the proof of this theorem, because the proof of this theorem is not a main topic of this course. Here we want to explain the numerical techniques for solving these types of initial value problems. But the proof of Picard theorem can be studied in the theory of ordinary differential equations. But here we do not want to study theoretically the ODEs, but we want to study numerically the ordinary differential equation, numerically ordinary differential equation. So it's not our main concern to discuss about the theorem of this, the proof of this theorem. So we will delete the proof of this theorem, but let me explain the main sketch of this proof. The Picard used recursive iteration process to prove this theorem. He defined a sequence of functions yn defined by using this recursive relation. Here, y0 will be y0x will be y0 based on our initial condition. Then yn can be obtained from this relation. Yn will be y0 plus integral of f of Kc and yn minus 1 when Kc is between x0 and x. Picard proposed this recursive relation to obtain this sequence of functions y0x to yn. Then in his proof he showed that this sequence will be converse uniformly on this domain, and a function y defined in this form will be the this procedure will be converged to a function called y and defined in this form. So in this proof, first, based on our initial condition, Picard defined this iteration. Then he proved that this sequence of functions yn will converge to a function y defined in this form. So, based on this procedure, he proved the existence of the solution. In the other words, the limit of this sequence of functions will be a function y satisfying the differential equation 1 subject to initial condition 2. This will be the existence of part of Picard's theorem. To prove uniqueness, he used the Lipschitz condition supposed in the theorem. So the proof of Picard's theorem will contain two parts. At the first part, he defined an iterative procedure to obtain a solution y. Then he used the Lipschitz condition to prove that this obtained solution will be the unique solution of this problem. So we have two parts. At the first part, we will check existence by using the Picard iteration. At the second part, we will study about the uniqueness of this obtained solution by using the Lipschitz condition. This is the main sketch of the proof of Picard theorem. I explained that just to review these details, and I explained that to you be more familiar with this proof. But the details of this proof is not the main, is not the concern of this course. This is the details of Picard's theorem, and now let me consider another example. Here we want to solve this initial value problem. This main ODE y prime equals the SQRT of x plus y over x minus y, subject to initial condition y at 0 equals 1. We want to check if this equation have a unique solution or not. To this end, we will use the Picard theorem. Here, this function will be our right-hand side function, and we will name this function f of x and y. F of x and y. This is our right-hand side function. This function will be continuous if the denominator of this function be do not equal to 0. In the other words, if we have x minus y, the denominator of this fraction be not equal to 0, then this function will be continuous. Also, to check Lipschitz condition, we will consider the first derivative of f subject to y. This will be in this form, and we can obtain an upper bound for this function. To this end, if someone consider this domain, this is the domain R have mentioned in the Picard theorem. In this domain, y will be different from x, and this condition will be satisfied. So, in this domain, for x and y, the function f will be continuous, will satisfy the Lipschitz condition, so we can resolve the unique solvability of or initial value problem. To this end, if we consider the maximum of function f will be less than 4, because the denominator of this fraction will be less than this value, and the denominator of this fraction will be greater than 1/3. So as a result, maximum of f will be less than 4. Now, if we consider these values of maximum of f, all of the details for Picard's theorem will be satisfied, and we can resolve this equation, ordinary differential equation, subject to this initial condition will have a unique solution. As a result, from this example, you can see if we have an initial value problem, uh, subject to this ordinary differential equations and this initial condition, then we can check the conditions defined in Picard's theorem to obtain the unique solvability of our problems. This is the first concluding remark from Picard's theorem. If we have Lipschitz conditions, continuity of our function f on obtained domain R, then our problem will have a unique solution. But you must consider this remark. A Lipschitz condition grants a unique solution, but in many problems we do not have this condition, but our problem maybe have a unique solution. For example, consider this problem. Here we do not have Lipschitz condition for this function, right hand function 3 times y over 2 terms. But this problem have a unique solution. In the other words, maybe in some problems we do not have Lipschitz condition, but this problem will have unique solution. In the other words, Lipschitz conditions just grant unique solution, but it's not the necessary condition. Here we have a function f. This function does not satisfy in Lipschitz conditions, but this problem, subject to this initial condition, have two solutions: y2 equals 0 and y of yt equals 0 and yt equals t q. So Lipschitz condition is the main condition for uniqueness of the solution, not existence of the solution. Okay. After this, do you have any question up to this section, dear friends? Is there any question? Do you have my voice? Is there any question? Mr. Al-Khafaji, unfortunately I don't have your voice. You can type. There is a problem with your voice. Okay, if you have any question, you can write here. But let me continue. The second result obtained from Picard's theorem is an approximate technique to obtain the solution of problems. This method will be called successive approximation or Picard iteration. This will be the first method we will study in this course. Consider this initial value problem, y prime equals f of t and y, subject to this initial condition, y at t naught equals y naught. If Picard iteration or successive approximations, we will use the right hand side function f subject to our initial condition. We will define with p dot equals y dot. Then we will use this recursive relation of phi I plus 1 will be defined phi 0 or y dot plus the integral from t0 to t of function f of s and phi I. Continuing this process and these iterations will result an approximation phi I. This is the famous Picard iterations or successive approximations. In Picard's theorem and the proof of Picard's theorem, if you consider the details, f function f satisfies the Lipschitz condition, then this procedure will result the unique solution of our initial value problem. This procedure will continue when n goes to infinity, but in practical situations we can use some limited number of iterations to obtain some approximation. In the other words, limit of the I, limit of the I, when I goes to infinity, will be the solution of the unique solution of our problem. But in practical situations, we can consider, for example, 10 iterations of this procedure to obtain an approximation of this solution. In the other words, for example, we can consider B10 obtained from this successive and from this recursive relation will be approximation of y. Y will be approximated by phi10 or phi20 or phi30 or phi25. All of these values will be some approximations of y. If our value considered for I be greater, then this approximation will be better. So someone continue this iteration for a finite number, then the obtained result will be an approximation of our solution. As an example, consider this problem. Y prime equals y. Y prime equals y, subject to this initial condition. Here, the right hand side function f, will be y. Here, f of t and y is y, t0 is 0, and y dot equals 1. Now we can use the Picard iteration defined in this algorithm. Here we have v0 equals y dot, so v0 will be 1 plus the integral from 0 to t of ds from this relation. So v that will be 1 plus t. Then again, by using this iteration, this iterate formula or iteration formula, we will have v1 equals y1 plus the integral from 1 plus s obtained in the previous step. Again, this result will be substituted in this relation to obtain v2. You can see we have these terms v0 1 plus t, v1 1 plus t plus t squared half, v2 is 1 plus t plus t squared half plus t cube over 3 factorial. So if we will use mathematical induction, we have this pattern for our unknown terms vi. By induction, you can see Vn equals this summation. So based on this Vn plus 1 can be obtained in this form. So Vn plus 1 will be this term. When someone obtain the limit of Vn when n goes to infinity, will result this infinite series. When n goes to infinity, this upper bound will go to infinity and result in this form. You can see this series of functions, and this will be the famous Taylor expansion of function Taylor expansion of function t of t. As a result, we obtain the exact solution of our initial value problem by using the famous Picard iteration. So here we used, let me explain again, we used the Picard theorem, a Picard iteration for this equation subject to this initial condition. Then when we obtain the limit of this terms Pn, results the final solution phi equals exponential of t. As another example, let me consider this problem. Here we have y prime equals 1 plus t times y. This is our in the right hand side function f of t and y. This is y dot. Based on the Picard iteration, we have y0 equals 1, y k plus 1 equals 1 plus integral of f of x and y. Here f of x and y will be 1 plus x y. So substituting f here in our iterate relation will result this integral. So from y0 equals 1 we can obtain, and substituting in this relation, we can obtain y1. Again, substituting y1 here, we can obtain y2. From y2, we can obtain y3, and so on. These will be some terms of Picard approximation or Picard successive method for obtaining this approximate solution of this initial value problem. Okay. This is the details of Picard's theorem and Picard's approximation. In the next session, in Saturday, I will focus on Picard's theorem for system of ordinary differential equations, and I will explain the details of this method. Also, we will continue our procedure to defining some new methods. After some details, I will start my explanation about Euler's method. But for this session, I think that's enough, and we can complete this session inshallah. In Saturday, I will continue my details about Picard theorem and the next topics of this course. Okay. Do you have any question, dear friends?
Thank you, Doctor. Now I have a question.
Okay, Mr. Al-Khafaji, I have your voice finally. Thank you, thank you. Okay, the other
Thank
friends.
Okay, Doctor, thank you.
Okay, you're welcome.
Have a nice day.
Thank you. Have a good weekend. I will see you again in the next Saturday.